Okay, we're on to Module 1.4 as part of the introductory series of video you're watching. This video particularly deals with the statistical underpinnings of distribution and habitat models. Now, I want to point out that I'm not going to go into too much detail here. This is just to give you a bit of a foundational basis because we'll be discussing each of the statistical tools that you use to build a distribution model when we get to that section. So what you're going to learn here is just some basic background on regression and classification. Also, a bit of overview of some of the available statistical classification tools. Now, there's lots of them. And as I think I've mentioned before, there is absolutely no way I can provide and introduce you to each and every one of these. But if you can figure out the five we work with in this course, you should be able to figure out the others as well. We'll also talk a little bit about how one goes about selecting a particular classifier to use. And of course, then as before, there's nothing associated with R in these introductory overviews and videos that you're watching here. So again, to reiterate something that we've mentioned several times already in this introduction here is why do we employ regression and in essence a subset called classification in ecological study? Again, we're trying to ascertain or portray relationships between a species and underlying ecological processes. Now, or at least I am in this class trying to motivate how you employ these particular classifications based on these four foundations of intended use. Why is a species here and not there? How is the species habitat relationship changing over time? Where is the species found? Those are the map products that we will learn to develop and deliver. And how much of the species habitat is there? Again, by exploring these foundations of your intended use before you move on into the actual modeling process is going to help you select the appropriate distribution and modeling tool to use. Now, the regression models themselves, they all differ according to the assumptions of what's called a functional form of the relationship between the response and the predictors. Now, I don't want to go into mathematics, statistical history here, or anything like that, but when you see the phrase functional form, what that means is there is something called a PDF. No, not the Adobe product, but what's called a probability distribution function. This is a mathematical relationship. And if something can be defined by that relationship, then there are certain things that you can do. The first derivative of a PDF is always the mean. The second derivative is the variance. It's an important component. Now, we don't go into math stat theory here, but just want you to understand if you see or hear me use functional form, that's what I'm referring to. Because this, in turn, defines the distributional assumptions about the data and themselves, the regression models will vary depending on what these assumptions are. Now, classification models are subsets of regression models. It has or they have the same underlying statistical characterization as above. However, the response, that is the functional form here, is typically binomial or it can be multinomial. Now, the model goal is to classify we often use predict, class memberships. And in our distribution modeling arena, the classification is typically focused on the species presence given the set of predictor environmental variables. Now, there are three general groupings of regression relative to classification models, and especially the classification models we use in a distribution model. The first of these are so-called fully parametric models. You all have been exposed to a general linear model as well as something called a generalized linear model. These are the models where that functional form is specified. There are different distributions. What this means is things are finite in terms of parameter estimates, but again, I probably shouldn't even include this right here. Just ignore it. The point is that there's a functional form. The second class is called semi-parametric models. These are often referred to as additive, and there's a class called generalized additive models. In this case, the functional form is only partially specified, tends to rely on estimation tools such as smoothers. Now, what do I mean by that? When you're in an additive model, instead of having a strict linear relationship, the direction of that relationship changes as you move across an x-axis. We'll see some examples of that as we do it. But again, the major thing to remember here is parametric models. It's fully specified. In a semi-parametric, only partially specified. Operationally, what that means is some of the variables in a GAM model, for example, actually have a functional form. Others do not. Whereas in a parametric model, all of the variables are assumed to have a form. The third class is what I generically refer to as non-parametric models. Now, there are a variety of different names assigned to this grouping, and some people even break it out into smaller subgroupings. I'm not going to for the purpose of this course. These are things that are so-called ensemble classifiers. These are often referred to as machine learning. They assume no functional relationships whatsoever. Now, the key thing you're going to walk away from, not so much here, but by the time we actually employ these different forms of parametric, semi-parametric, and non-parametric models, is that each have strengths and each have weaknesses. Hence, as I've mentioned several times in this series of introductory videos, you want to avoid any generalizations that one of these is best. Remember, you're searching for a useful model that will help you achieve the intended uses that you have articulated for the model. And in some cases, that might be a parametric model, others a semi, and in some case, a non-parametric model. So again, you are looking for which of these models that is going to help you meet your intended uses. So here's our simple and multiple linear regression. You've all seen this particular equation, y equals mx plus b. Okay, this is just the form. Intercept, beta variables, and this. Y is the response, alpha is the intercept, predictor variables, and the regression components, and this represents the error. You don't need to memorize this. I'm just showing you because you'll see how these model forms change as we move from parametric to semi. So Simple and multiple linear regression are parametric models. Now, of course, what we're doing right here is looking at an independent X, a dependent Y, and if there's a model, if there's no model, you got a flat line. If this line right here deviates from flat, then you have a model. And there's a variety of error. This is the prediction. This is the observed. That's the error. This is the model error, which is the how it deviates from the flat line. Now, the reason I show you this is all of these models have this error component right here. The predicted versus the observed. How it's portrayed depends on the model form. This is a parametric display of error like this. Because what happens is that if you have a prediction here and an observation here, you have a large difference. Prediction here, a not so large. Prediction here, a small. Think Goldilocks here. Not too hot, not too cold, perfect for something like that. Now, the error, when you sum up all of these things right here, translates into measures of the model fit as well as its predictive capability. Now, all of these types of models can predict even when large differences between the observed and the predicted exist, but then the model fit and its reliability are low. So this constitutes how one views parametric models. Now, a generalized versus a general is just a mathematical extension of the linear. Now, this allows for non-linearity to occur. Now, what GLMs do is they extend the linear model in two ways. The first, the expected mean, that's this. Whoops, that's this right here. And the linear combinations is expressed through a different function that's called the link. The link changes the mean to something else. So that means there's a flexibility in the distribution assumptions. Now, what it looks like is this. This part of the model's the same as a simple linear. This is the same, and all we've done is put something on the outside. This outside here is the link. Now, common link functions are log, the logit, and to be frank, if you identify a link called the normal, you have a simple linear regression model. So this is the normal right here. So what you learned in school about simple linear regression is it is actually a generalized linear model with an expectation that distributions are normal. In our world of trying to classify into one of two possible classes, our link function becomes binomial, or what they call the logit. And so this changes. So all you're doing is swapping out this normal distribution with this log through this part right here of the equation. And then that allows us to not deal with continuous variables, but discrete response variables. And the discrete response variables in a classification tool, a distribution modeling tool, is either a 0 or a 1. Well, you can use whatever it is. It's just two choices. Now, the GLMs allow for a lot more flexibility As I said, there's all sorts. You've got Poisson. I'm sure have people heard of Poisson regression, negative, gamma, inverse like this. We're, of course, in a classification going to deal with this. Now, simply stated, to reiterate, the link function replaces the expected mean. This is the expected mean with something else. And in our case, we are going to be using the logit link because instead of a continuous expected response, we are going to have a binomial expected response. Now, here's how the error is portrayed. Now, this is a logistic model with the binomial link. Now, a perfect fit, I don't want to mess up my graph yet, is going to be a absolutely perfect step function from 1 to a 0 down here. However, we have error. So what we have here is a predictor X and a predicted response Y. And notice this curve, the red right here. This is based on the observations. All these red dots right here represent the the predicted values that we saw here, here, and here. It's just in a different form. Now up here and down here, we have the observations for 0 and the observations for 1. And here we have kind of a point of inflection. Remember previously when I mentioned thresholds and their influence on a model? Well, here you have it. This inflection point is a threshold because anything on this side basically gets classified as a 1. Anything on this side gets classified as a 0, which leads to error. So what we have here is an observed down here of 0, but its predictor value of 31 says it should be up here in what is classified as a 1. So notice then that we have a large error that is associated with this. Over here, notice we have small errors, but we have large errors up here because some of these observed values of 0 actually have a predictor that makes them likely to be 1. So in essence, this is the error, and this is the type of error you're going to see in these types of models. Because all these large and small differences, they're going to sum up. They're going to give a measure of fit. And then they're also going to assess predictive capability. All of this error translates into the accuracy and assessment metrics that we're going to see as the course progresses. Now, in the class of ensemble and averaging classifiers, these are basically called tree classifiers. So what it does is it takes the predictor value X, it takes the 0s and the 1s, and it moves up and down here until it finds what's called a cut point that maximizes membership here and maximizes membership here. This becomes a node in the classification tree. And so you tend to see these types of structures. Now, these tree-based models, which I generically define as non-parametric, these are the most common types of models in the non-parametric grouping. We have boosted regression trees. We have Bayesian additive trees. We have random forest trees. we have classification trees. So as you can kind of see, these are these different ways we're going to be approaching it. And all of these models, based on the three, this is going to be the basic underpinning of the non-parametric. This is going to be the basic underpinning of the parametric models that we're dealing with. But these then are how these particular types of tools are going to work. Now, we're at the end here, and there's no exercise associated. But what I want to do is re-emphasize something, and that's that we're going to come back and explore in a little bit more detail the characteristics of things like this versus the characteristics of things like that. So that by the time you finish working with logistic regression, you'll have a complete understanding of how this works. By the time you finish working with random forest or boosted regression trees, you'll have an understanding of how this works. I strive, it's a really tough to find a balance in what is a zone of tension here of a zone of tension between too much and not enough. But I shoot for you to have what I call lay person's understanding, so that if a decision maker asks, you can at least speak coherently. Do you have to understand all the gory mathematics? Absolutely not. But you do need to know that we replace a normal distribution with a logit to generate this, and a classification tree runs up and down a predictor level till it maximizes membership in one group and maximizes membership in the other. With that, we're going to go ahead and end this module 1.4. Like I said, I don't want to dive too deep into this since we'll be spending a little bit more time on the underpinnings of each of the tool as we actually implement the tools to build your distribution models.